Hello once again, class, and welcome to another mock lecture. Today we are going to be tackling one of my favorite topics in differential calculus, which is related rates. So let's get into it. You see, at this point, we pretty much know most of the differentiation techniques that we need for the remainder of the calc series. I guess the one exception being partial derivatives, which you'll talk about when you do three-dimensional stuff, but everything else, we pretty much know. We know logarithmic differentiation, we know the derivatives of all the basic trig functions and exponential functions and chain rule, product rule, quotient rule, power rule, and all that stuff. So now it's time for us to do some cool application stuff, beginning with related rates. So for today, what we're going to be talking about is how are things changing with respect to time. Now you might have noticed in your years of learning and studying math and science that time is a bit of a universal denominator when you're examining rates of change. For example, if you're at an infusion, an IV infusion, a drug is pumped into your bloodstream at some amount of milliliters per hour. If you're talking about the velocity of an object, right, that's a kilometer per hour. For population growth, the delta of population, the change in population per year, right, is something that's going to be important to look at. Or if you're in the middle of a pandemic, talking about the number of new cases per day might be something that you want to talk about. And each of these things, time is a denominator, right? Milliliters per hour, kilometers per hour, change in population per year, number of new cases per day. Our goal today is to relate these rates to something else. Many rates can be related to another rate of change, using time as their kind of connecting variable. For example, an IV, right, milliliters per hour, this could be related to the percent of blood in the bloodstream that's carrying the drug. Velocity can be related to the velocity of another object. Maybe you're tracking two different objects. Population growth can be related to resource growth or resource management growth. And pandemic stuff, number of new cases per day, can be related to a death rate or a vaccination rate. And the common denominator, the thing that all of these rates have in common is time. The variable that connects all these rates is time. To actually relate them, though, you need to find an equation that relates their base quantities first, right? Their main variables first. You also need to be comfortable differentiating with respect to time. And this is somewhat new. I mean, we know how to differentiate, for example, y with respect to x. That's implicit differentiation stuff. But today, we're going to be doing some implicit differentiation with a variable t, and the variable itself, t, isn't going to show up in the equation at all. Here's a quick example. No, stop. It's not this. I don't want to do this yet. Okay, this is just a quick one. If we differentiate both sides with respect to t, which means that we're using d dt, right, derivative with respect to t. Notice there is no t in this equation at all, so we're actually treating both y and x as some function of t. So if you think back to when we were doing implicit differentiation with respect to x, y, right, the d dx, right, of, I don't know, like a y squared, let's say. So it's actually not this. What we had to do was say, oh, this is 2y, but then also multiply by y prime. Well, same sort of thing is going to happen here and here, right? And that's the new part. This is now happening for x as well. X cubed is going to involve the chain rule, right? When you're differentiating it with something, in terms of something else, right? In terms of something that's not x. So we use implicit differentiation and we get dy dt on the left. We get 3x squared over 2, which is the normal derivative of x cubed over 2. But then you have to multiply by the derivative of x, and that's dx dt. Now these rates are related. The rate at which y is changing is now related to the rate at which x is changing with respect to the time variable. I like to actually think about related rates as kind of like a cog system. So time, when you turn the time cog, it's turning both y and x at the same time. No pun intended. But that's how we're relating these two rates, with a common cog, if you will, t being that common cog. That's at least how I think about it anyway. By the way, and I think that this is an important note, before when I was doing the differentiation over here, I was using stuff like y prime. You actually don't want to do that when you're differentiating these, when you're finding the related rates equation. Reason being is because when you look at y prime and x prime, we don't know what these things are in terms of. So instead of doing this, you really want to use dy dt and dx dt because it's much more informative. It allows us to see what the derivatives are in terms of time. And that's the main thing. Like the thing that it's informing us is, oh, these are derivatives in terms of time. Time is the variable that we're differentiating with respect to. The other important thing to keep in mind is that in order to relate rates at all, right, and we said this a little bit ago, but you have to have an equation that already relates x and y. And oftentimes I find that part is the most difficult part of doing related rates. What is an equation at all that will relate our base variables so that we can just differentiate them with respect to time, thus relating their rates? So now, let's get into some examples. All right, example number 1. Suppose a stone is thrown into a still lake and creates a ripple that spreads on the surface of the water. This thing, by the way, is called a capillary wave. And let's say that the capillary wave is spreading at a rate of 2 feet per second. Okay, so we've thrown a stone into the water, the ripples emanating outward from the center of this thing at a rate of 2 feet per second, which means that its radius is changing. It's increasing 2 feet every second. What I want to do is I want to figure out how fast is the area enclosed by the capillary wave increasing when the radius is 6 feet. One thing that I probably should clarify is that we're assuming that it spreads at a constant rate. Constant should be right there. The word constant should be there. So even when the radius is 6 feet, the radius itself is still increasing at 2 feet per second. What we want to do is we want to figure out, well, what's the area enclosed by this wave? How fast is it increasing when the radius is 6 feet? So there's a couple steps that I go through when I'm solving related rates problems. The first thing that I look at is, what information am I given? What information do we want to find? So I'm going to go through this paragraph again, and I'm going to just pick out some information that we know. First, we know the radius is 6 feet, and I've actually kind of already drawn that on my top-down view of the wave now. We also know that dr dt is 2 feet per second. That's probably important. I don't think it's going to show up on other slides, but it is a rate in terms of feet per second. We need to find dA dt. Right? We need to find how fast the area is increasing when the radius is 6 feet. So we don't know that particular rate. The next thing I do is I need to find an equation that relates these kind of base variables that we have. In particular, in this case, we have an area and we have a radius. Well, in this example, that's just the area formula for a circle. Area is related to radius by way of the area formula for a circle. A is equal to pi r squared. So that's going to be the thing that we're going to need to differentiate with respect to t, which is my last step. Lastly, we differentiate with respect to t, which is our time variable. So let's do that. I wrote a is equal to pi r squared. I'm differentiating it now with respect to t. So that's going to give us dA dt, which is the derivative of a. I brought out this pi because it's a constant, so I just need to differentiate r squared with respect to t, which gives me 2 pi r dr dt. And now our rates are related, right? We have a rate of change of area with respect to time, we have a radius variable, and we have a rate of change of the radius, which we are given to be 2 feet per second. So at this point, I just plug in the info that I know, right? I know r is 6, I know dr dt is 2, so I plug this information in, 6 feet, 2 feet per second. So when I multiply these two things together, we're going to get square feet per second. That's something to notice at this stage. And so we get 24 pi square feet per second. That is how fast the area that's enclosed by this capillary wave is increasing. Now, of course, I could actually just do the multiplication there. It's like something like 78 square feet per second. I don't know. Multiply 24 by pi. But there you go. That's our first example of related rates. Let's do another one. A 12-foot long ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 5.5 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 7 feet away from the wall? So first I drew a picture. Here's our picture of what's going on. This is the 12-foot ladder. I'm going to call the vertical height of the ladder B, the horizontal distance away from the wall A, and we know dA dt. is 0.5 feet per second, right? It's sliding away at a rate of 0.5 feet per second. And what we're trying to do is figure out, well, then how fast is this ladder sliding down the wall? So right away in my head, I'm like, okay, well, our answer is going to be negative because B is shrinking. We don't know dB dt. That's what we're trying to find. And then we also know that we're given a horizontal distance away from the wall that we need to use, and we're given a horizontal distance that we need to use for how far away this ladder is from the wall to start with. We need to find an equation that relates A and B so that we can differentiate it with respect to time, thusly relating dA dt and dB dt. Well, in this case, that's just the Pythagorean theorem. Okay, so that's where I'm going to start. I blew up this picture a little bit. Let's move the ladder to where it's 7 feet away from the wall. We know dA dt is 0.5 feet per second. We're trying to find dB dt. And the thing that relates A, B, and this 12-foot ladder is indeed the Pythagorean theorem. Also, I didn't make it clear in the drawing before, but this is definitely a right angle that we're talking about here. So I plugged in 12 for this thing, and then I differentiated it. I plugged in 12 for C, and then now I'm differentiating it with respect to time. And the reason I plugged in 12 first is because I don't want a dC dt. There's no rate at which the ladder is changing its length. It's always 12 feet. So when you differentiate it with respect to time, it's still a constant. And so we're going to get 0 on the right-hand side. Differentiating a squared and b squared is exactly the same when you're differentiating with respect to a t variable. You get 2a dA dt and 2b dB dt. At this point, you could actually isolate dB dt. I didn't for some reason. I actually don't know why. I definitely could have done that here. But instead, I just plugged in my known stuff at this point, which we know a to be 7, and we know its rate to be 0.5 feet per second. So I plugged that stuff in. But you'll notice that we actually still can't solve for dB dt. We don't know b. We're solving for this. This is something we don't know. But we can take this triangle that we've created and we can solve for b just using the Pythagorean theorem. Right? In this triangle, b squared plus 7 squared is equal to 12 squared. Doing some math gives us not 9.75, but it's approximate. It's like 9.746, some stuff. So I'm definitely approximating here a little bit. But I got 9.75 feet is b. So I plugged that in, and now I can solve for dB dt. So I just did some algebra. 2 times a half is 1. So I just was left with 7 there. 2 times 9.75 is 19.5. I subtracted the 7 and then divided by 19.5, so I got negative 0.36 feet per second. Which means that the answer to our question, and I don't think I wrote this down, but the answer to our question would be, well, the ladder's sliding down the wall at 0.36 feet per second. So one of the things that I think students find the most challenging, I mean, when I learned this was the most challenging thing for me, is what is the equation that I need to differentiate with respect to time so that the rates I want to relate actually get related, right? I feel like that's the hard part. Differentiating is actually the easy part, right? Plugging in numbers and calculating is what I consider to be the easy part. The hard part of this thing is figuring out, well, what even is the equation that I should use to relate my base variables so that the rates that I'm looking at are also going to be related. Most often, and I guess I shouldn't say that. I should say oftentimes, not most often, but it very typically happens that you're allowed to rely on known formulas. Like in our first example, we relied on the area of a circle formula. That related our variables and thus the rates that we were looking at. In the last example, Pythagorean theorem, right, is the theorem that we used to relate our variables and thus our rates. Here's another one where we can rely on a geometric formula to relate our base variables such that when we differentiate it with respect to time, that our rates will be related. Suppose a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute. Find the rate at which the radius decreases when the radius is 7 centimeters. The idea is you got this snowball, it's slowly melting, and what we're trying to do is figure out how fast the radius is decreasing, right? How fast is the radius of this thing decreasing per minute? So we have surface area and we have radius. Those are our two main values that we need to try to relate. Well, we can just use the surface area for a sphere formula, which is A is equal to 4 pi r squared. At this point, you're just going to differentiate, right? dA dt is equal to 8 pi r dr dt. And then you just plug in known information. We know the rate for the surface area is -1 square centimeter per minute. We're looking at when the radius is 7 centimeters, and we're trying to solve for dr/dt. So you get -1 over 56 pi. But what is the units? What are the units of measure in this case? Let's analyze this actually a little bit. So we've got -1 centimeter squared per second. 7 is just a length. It's in centimeters. So here you have square centimeters divided by centimeters, which will cancel. And so you're just going to get centimeters per second, which makes sense. Radius is a length. It's just a distance. So we're not decreasing in area here. It should just be a linear change per second. And it is -1 over 56 pi centimeters per second, which is really slow, I think. So we'd say, because I don't know what -1 over 56 pi is, but I think it's pretty small. That's like -1 over, what is that, 170 something? That's a small number. But anyway, we'd say the rate at which the radius is decreasing is +1 over 56 pi centimeters per second, because we're using the word decreasing. But we could say that it's changing at -1 over 56 pi centimeters per second. All right? Now, there are a lot of examples that we could do with related rates, ranging from stuff like what we just did, where a known geometric formula kind of helps us relate the variables that we need to relate their rates for, to really, really complicated looking stuff. And if you're taking my class in person, we'll talk about a wide range of these things. If I have time, I may even make another example video about a related rates problem. That's what I feel is like higher, like upper echelon sort of difficulty. But for now, I think I want to focus this video mostly on the idea behind it. You need to find an equation. You need to know what you want to relate, first of all. Then you need to find an equation that will relate those variables, differentiate it with respect to time so that their rates will be related, and then plug in known information and solve for the rate that you're looking for. So hopefully you guys learned something. If you have any questions, please shoot me an email or leave a comment below. Thanks a ton for watching, and I'll see you in the next one.